And there's one more thing that I want to look at in terms of thermodynamics, which is actually covered in the transition metal chapter. And this is further proof that as we start moving along in chemistry, that we use different branches of chemistry to solve problems and to give explanations for criteria that are happening in the lab. And the effect in chapter 24 is something called the chelate effect. And a chelating ligand is sometimes a nickname for a bidentate ligand. Okay? So what we can say about this, and we have to look at entropy to enable us to come up with a rational explanation for this. So the spontaneity of a chemical process is favored by a positive change in entropy and or a negative change in enthalpy. So we can say that delta G naught is equal to delta H naught minus T delta S naught. There's two effects that we have to take into consideration. We have a driving force to make it spontaneous by the enthalpy and a driving force from the entropy. The special stability or the special case associated with the formation of chelates called the chelate effect can be explained by looking into the entropy change occurring when polydentate ligands bind to a transition metal. So we're going to consider two different reactions. The first reaction we're going to consider is if we have Ni H2O6 2 plus in aqueous solution. When we take this ion in aqueous solution and we add 6 equivalents of ammonia, it's going to be in equilibrium with Ni NH3 6 2 plus 6 waters. If we look at the formation constant for this reaction, or the Kf, it is 1.2 times 10 to the 9th. We have a very, very large formation constant. Delta G is going to be equal to minus RT ln K. Since K is large and positive, delta G is going to be large and negative. This is going to be a spontaneous process under standard conditions. If we look at, and I'm going to leave a little bit of space here, in the process number 2, or our second reaction, we're going to take the same starting complex with NiH2O6 in aqueous solution with a 2 plus charge. we're going to add 3 equivalents of ethylene diamine. And this is going to be in equilibrium with NiEN3, because remember, ethylene diamine's a bidentate ligand, so to form an octahedral complex, we only need 3 of them, plus 6 H2O in aqueous solution. And in each case, I'll point out that we're saying that the water is aqueous species in solution because they were displaced off of the transition metal, and it's not like water as a pure liquid in that solution. The Kf for this particular equilibrium is going to be 6.8 times 10 to the 17th. Dramatic difference. The question we need to answer now is why are these 2 guys so dramatically different? So chemists looked into this and they say, okay, the equilibrium constant is related to some of these thermodynamic quantities. So if we look at a particular thermodynamic quantity, we know that delta G naught is equal to delta H naught minus T delta S naught. If we look at all the species on the left-hand side of each of these equations, for reaction number 1, we have 7 moles of aqueous ions in solution. That's going to be on the reactant side. On the product side, we also have 7 moles of aqueous ions in solution. So we can roughly approximate the delta S naught to be equal to 0. Because we have roughly the same number of moles, the species are very similar. It's going to be close to 0. For reaction number 2, on the reactant side, we have 4 moles of aqueous ions in solution as a reactant, and in the product side, we have 7 moles of aqueous ions in solution. When we go from 4 moles to 7 moles, we said that the standard entropy is going to increase. If our entropy increases, that's going to make our delta G more negative. So let's kind of analyze these in a little bit more a thorough detail. For reaction number 1, we know that delta G naught is equal to delta H naught minus T delta S naught. If we approximate the delta S naught to be equal to 0, this term goes away. So the delta G is going to be proportional to delta H. Okay? We have a large K, so that's going to mean that delta H has to be negative, or we have an exothermic reaction. In reaction number 2, we see a huge increase of that formation constant. So what that also tells us is that the delta H naught is also negative. And we also know that the delta S naught is going to be positive. So if we have delta G naught equaling delta H naught minus T delta S naught, and this is negative and this is positive, this is driven by enthalpy and entropy. In the case of scenario number 1, we know that this is driven by enthalpy, but not entropy. So we have an entropy term that we have to look at and an enthalpy term. if we have a really, really large value for delta G, the spontaneity of the reaction is going to be driven by both the entropy and the enthalpy. We have that in case number 2. Whereas in case number 1, it's just the delta H that will drive that reaction forward. So this is why we see a large increase in the Kf value, or the formation constant, for this particular reaction. Okay? So